What's up, my students? So here is a video on, well, if you read the title, you should know what this video is on, but I will let you know that this video is on, I can't remember myself. We are talking about Vesper, and we're talking about, yes, we're talking about polarity. Okay, so this is talking about polarity with large molecules. So in class, we talked about how for smaller molecules with just one atom attached to another atom, we can simply just take a look at their dipoles to see if there is a dipole. If there is a dipole, the molecule must be polar. If there isn't one, then we can kind of assume it's nonpolar. So that was very simple, but with these larger molecules, we have more than a single atom to compare to. Okay, so we might have like, for instance, CH4 methane. We have a carbon and we have four other hydrogens. It's not just a single hydrogen compared to a carbon. Okay, it's four other hydrogens you have to take into account. So this is where things get a bit tricky. Okay, so first of all, in order to kind of rehash on what a dipole is, a dipole is simply when we have an electronegative atom, okay? When we have an electronegative atom that sort of wants to hog the electrons more, more closely to itself, okay? That's gonna create a, I'll draw it out here. We have a brush, and let's brush away with some green, okay? Let's see how this works. All right, so if this was a hydrogen atom, okay? And this was, no, let's not make it hydrogen. Undo is Control Z, Control Z. Okay, if this was a oxygen atom, and this was a carbon atom, this is an oxygen atom. Let's just take a look at these two guys over here. This carbon atom is less electronegative than this oxygen atom. Hence, this oxygen, when they share electrons, it is a covalent bond. The electrons are going to be more closely near oxygen. So this is going to create a partially negative charge, and this is going to be a partially positive. You see more electrons kind of hanging towards oxygen. So since electrons are negative, we're going to have a slightly partially negative charge. So this is a dipole. Okay, think two poles. Okay. Now for larger molecules, we're going to have to compare the dipoles for all of the bonds associated with the center atom. Okay. So let's just do CO2 for example. Okay. CO2. Now for this carbon and this oxygen, we know that the dipole is going to be going this direction. This arrow just means that the electron is closely, more closely associated with this oxygen compared to this carbon. Now with this oxygen, same thing. We have a partially negative charge, so the dipole is going this way. This is what I mean by indicating dipoles, okay? Now, if you were to take a look at this, we have some sort of force, okay, some sort of pulling force over here, some sort of dipole going on here. Would you guys agree that this dipole, from this carbon to this oxygen atom, is the same as this carbon to this oxygen atom? Give you guys 2 seconds. And yes, you guys should have agreed. So because they're pulling equally, this carbon's going nowhere, okay? These dipoles are being canceled out, okay? Whenever you have something that's being canceled out, we call this I don't even need to write it down, but we call this non-polar, okay? When dipoles kind of cancel out, it's non-polar. Now this was an easy example because carbon dioxide is a linear molecule. But if we take a look at something else that's a little more tricky, like this guy over here, like a tetrahedral. Okay, so we have a tetrahedral shape going on over here. Let me put this over here. We have a tetrahedral shape, okay? Right. Now, initially you want to draw the Lewis structure. Okay. However, because I need to write with my mouse, I won't draw Lewis structure. Let's just do an example for CH4 methane. Now I know there's gonna be some of you guys who think that if you just draw a Lewis structure, you can just figure out whether it's polar or non-polar. And some of you guys may be able to do that, and that's good. But my suggestion is always draw the 3D shape, okay? Even if you think you're confident, okay? Just because, my period 3 students, just because you can throw a piece of paper into the trash can using your fancy crossovers and whatnot, right? Doesn't mean you can do that on the actual basketball court. So, okay, that analogy wasn't so great, but what I mean is just because you think you're good with 2 dimensions, okay, doesn't mean you shouldn't observe the 3-dimensional figure. Okay, it helps a lot when trying to figure out polarity, when you actually can visualize the 3D figure. You can even draw it out if you want. Okay, so here's a 3D figure for a tetrahedral for CH4. Okay, now we have H is over here, H is over here, H is over here, and H is over here, and we have a carbon in the middle. So now we're always looking at the central atom. Okay, so from this central atom to all the other hydrogens, let's figure out the dipoles. Let's indicate the dipoles. Okay, so between hydrogen and carbon, carbon has more higher electronegativity, so we have a dipole moment going this way for this bond over here. For the carbon atom here and this hydrogen atom over here, same thing. It's going towards the carbon. Okay, so we know that each of these bond angles are 109.5 degrees for a tetrahedral shape, and it's like that for every single bond. So this is as even as it can get. This is a standard shape. So if you have hydrogens that are kind of pushing, or not pushing, this carbon that's pulling hydrogen's electrons equally for all sides, the dipoles, they cancel out. These dipole moments, these arrows, they sort of cancel out. If you cancel them out, if this carbon's not going anywhere, then we have a nonpolar. Okay. Now, if you were to, let's do another example. Yeah, another example would be CH3. Oops, I didn't need to erase that, but okay, let's watch me erase. And we do CH3O minus, like so. Okay, this is also going to yield a tetrahedral shape. Okay, so this is C and then H, H, and then H. I'm just going to call the top one O. Okay, this also yields a tetrahedral shape, but let's take a look at the dipoles. So again, for the hydrogens, we have dipole going this way, dipole going this way. This just means that the electrons are closer to the carbon. Okay, while this bond is occurring, the electrons are closer to the carbon. And for this, between carbon and oxygen though, oxygen has a higher electronegativity. So the dipole is going to tend to go up. Okay? So now let's take a look at these arrows for a second. And even if you don't look at the arrows, just kind of look at how the polarity is shaped here. So if you have a dipole moment going this way, that way, and this way, we kind of want to have something to balance this out, to kind of make everything cancel out. But in this case, we don't. In this case, we're even going upwards. So this dipole over here, this net dipole, it's ultimately going some other direction. Okay? Because it's not staying still, the dipoles aren't being canceled out. This is called polar. Okay? Good. So with predicting polarity, you really, really have to envision or visualize these molecules in 3D. Okay, you can draw them out if that helps you, but please, I highly, highly don't recommend you just base this off the Lewis structure. Because let's just draw the Lewis structure for a second. We have C in the middle, and H, and H, and H like this, and then O. Okay, O like that. Let's do the electrons. Let me do that. Okay, this kind of looks symmetrical, right? If you just kind of cut this in half this way, okay, it looks symmetrical. Okay, so you can really never tell, the polarity until you make this 3D shape. And for those of you guys who don't need to and you're doing fine, that's great. But for most of you guys, or for some of you, this will greatly help. This helps me a lot. Okay. All right. Thank you for watching. This has been too long. Have a good day.